grabación. I click on recording instead of broadcasting. Connection excellent. Okay. Let's see. Okay, perfect.
Well,
Live.
perfecto.
Okay, that's the sound for this. Okay. And you will probably want to know. Let me see.
Ah, sí, gracias.
Trying to see how. Okay. So I put. Is that information enough for you to know more or less what you are getting?
Yeah, perfect.
Okay.
Great.
So,
Thank you.
if everything is okay,
Ah, cool. I'll pointer.
you have a green pointer here, and this for
That's great.
switching flights.
Thank you very much.
Everything is okay. We are set.
Great. Voilà.
Luego me clases, cógeme esa, voy a
¿Y podemos mover el cursor? Aquí. ¿Podemos quitar? Eso. Perfecto. Gracias, Miguel. Claro. Estoy bien, sí, gracias. Yes.
So, good morning everyone, welcome to our APARCOS-UCM. This is the last seminar before the summer break, and today it's my pleasure to introduce you Luke Holden. Luke began his undergraduate degree in physics and astronomy at the University of Sheffield in UK in 2015. As part of this degree, he undertook an employment experience here at the Isaac Newton Group of Telescope in La Palma, Canary Island in 2018. Where he served as both as a research student and support astronomer for the 2.5-meter Isaac Newton telescope. He returned to Sheffield in 2019 to complete his master's degree, during which he was awarded the Tom Kaiser Award for the best appreciation for the subject of astronomy. In 2020, he started his PhD at the University of Sheffield under the supervision of Professor Clive Hunter. His research focused on detailed studies of AGN-driven outflows in nearby galactic galaxies, resulting in 4 first-order publications. After completing his PhD in 2024, he joined the University of Hertfordshire for a postdoctoral research, where he currently works with Professor Dan Smith and his team on the forthcoming WEAVE-LOFAR survey. His primary research interests lie in understanding the nature and impact of outflows driven by AGN on their host galaxies. Today, Luke will present his talk, Galaxy Scale AGN Feedback in the area of the largest spectroscope. Oh, sorry. No, no, okay.
Great, don't worry. Good. Well, thank you very much, Luca. Y primero, quiero decir muchísimas gracias por invitarme a dar esta charla. Es un gran placer estar aquí. Y agradezco mucho la oportunidad a hablar con vosotros sobre el trabajo que estamos haciendo en Hertfordshire. For those of you who don't speak Spanish, thank you very much. My name is Luke Holden. It's a pleasure to be here. Thank you very much for inviting me to give this talk today. I'm really excited to show you some of the work we've been doing at Hertfordshire and what we're planning to do, particularly when this new big thing called WEAVE-LOFAR comes online in hopefully a few months' time. So what we're talking about, as Enrique kind of mentioned, is galaxy scale AGN feedback in the era of upcoming large spectroscopic surveys. And the main thing we're probing here is galaxy evolution. So just to start, what do I mean by galaxy evolution? So I'm defining galaxy evolution here as quite simply being, how do galaxies, or their properties of galaxies, evolve over cosmic time? So since the Big Bang, how has the gas contents and stellar contents of galaxies changed? Now, to start with a very broad question, why should you care about this? Right? If you work on, I don't know, exoplanets or star formation or anything, why should you care about how galaxies evolve? Well, I make the point that basically, well, almost everything in astrophysics that we're interested in happens within or around galaxies. So if you're interested in star formation, the properties of the clouds that stars form from will be influenced by how those gas clouds have evolved in those galaxies, or rather how the gas contents of galaxies has evolved over billions of years. Then obviously, how those stars form from those gas clouds impact how those stars evolve and impact how planets around them form. And similarly, if you're interested in exotic physics, things like black holes, well, we find those in galaxies, right? So galaxy evolution has an impact on virtually every area of astrophysics. And particularly if you're a cosmologist, that's been working with things like DESI, then still you will be using galaxies in some way as a probe of properties of the universe. So it's important that we understand how they evolve. So when, as observational astronomers, we look out into the universe at real galaxies, we see that a fraction of them have incredibly bright centers. So here are two very typical examples of two such galaxies, NGC 1068 and NGC 4151. And we can see in these images that there is something very, very bright happening in the centers of these galaxies. In fact, the events happening in the centers of these galaxies are brighter than the integrated brightness of the host galaxies themselves. And as you can see, they're very, very compact. So we call these things active galactic nuclei, or AGN. And again, we have something very, very compact happening, kicking out a lot of energy. So what is this? If we have a lot of energy, maybe that can impact how the galaxy evolves, right? It can impact the properties of the host galaxy itself. So it's commonly accepted now that these AGN, again, these compact regions of immense brightness and energy in the centers of galaxies, in some galaxies, is powered by accretion of gas onto supermassive black holes high. So this is a typical schematic of what we'd call an AGN, an engine, so an active galactic nucleus. So in the center of a galaxy, we'll have a supermassive black hole, or SNBH. So supermassive black hole here, I'm defining as a black hole that has a mass of above 10 to the 6 solar masses. You have gas accreting onto the supermassive black hole, and as the gas accretes onto the supermassive black hole, due to the conservation of angular momentum, that gas settles into a disk, and then the gas in that disk spirals inwards and eventually is accreted onto the supermassive black hole. Now, as this happens, because we are in an extreme gravitational environment, the dynamical forces that are being pressed onto that gas are extreme. And that causes an extreme amount of, you can think of it as dynamical friction, which heats up that gas to incredibly hot temperatures and ionizes it. So that means we have extremely hot ionized gas circling around the central regions of galaxies around these supermassive black holes. Now, because that gas is very hot and very ionized, that means it starts to emit very, very brightly. And that is the source of the extreme optical brightness that we see in AGN, in the central regions of some of these galaxies. Now again, because we have highly ionized gas in its accretion disk, that means we have magnetic fields, which we know from electrodynamics. And because we have a supermassive black hole, which is an extreme gravitational environment, it means that the magnetic field lines are spun up around the spin axis of the supermassive black hole. And then the ionized material in the disk is launched along those spin lines in a very, very fast, highly collimated structure of plasma, which we call a jet. So these jets we observe reaching from anywhere from hundreds of parsec scales out to almost megaparsec scales, so they can extend far beyond the extent of their host galaxies. And again, these are very highly collimated streams of plasma moving around velocities of 0.1 c, so about 10% the speed of light, so incredibly fast. So you have this incredibly energetic system in the centers of some galaxies in a very compact area. It's worth mentioning here, we have what we think is an obscuring structure of gas and dust that we call the torus. And what this basically means is the observed properties of an AGN depend on how we view it. So inside this torus, we have what we call the broad line region. That's because we see broad emission lines in this region, which indicate highly moving gas, high velocity gas. That's simply due to gas which is close to the supermassive black hole and has high velocities. And then further out, beyond this torus, we have what we call the narrow line region. So this is less kinematically extreme gas, typically following the rotation of the host galaxy. And again, this is ionized by either radiation from the accretion disk or via shocks driven into the interstellar medium by the jet. And if we're looking at the system from the side, then we call this a type 2 AGN because we don't see the broad line region and we do not see direct emission from the accretion disk because it's obscured by its torus. Whereas if we're looking at this sort of down from the top or at an angle, we call this a type 1 AGN, in which case we see everything. The narrow line region, the broad line region, and the emission from the accretion disk. So again here, we have an incredibly powerful system in the center of a galaxy. And since we think that most, if not all galaxies host a supermassive black hole, then we would expect that almost every galaxy will undergo several phases of AGN activity in its lifetime. So that's an extreme amount of energy that can be put into host galaxies over cosmic time. So we expect these things to impact the host galaxy in some way. And we do indeed see a lot of observational evidence of this on various scales. So if we look at the luminosity function of galaxies, so this is basically stellar mass against luminosity. You can think of this as a histogram of galaxy stellar masses. We see here that if we just run a simulation with no impact of these AGN, we get this black line, which completely overpredicts the amount of massive galaxies compared to the observed relation. And the only way we can explain this is if we implement impact from this AGN in our simulations, in which case it reduces the amount of massive stars and reproduces the observed relations. Similarly, we see in galaxy clusters very highly ionized gas emitting X-rays that's very high temperature. We would expect over billions of years, this gas would cool down and form stars in the host galaxy. So we should not be seeing this hot X-ray emission. It should have cooled by now. So the fact that we see it indicates that something is keeping this gas very hot and ionized. And what we think this is are AGN jets. So an AGN here with the jets being from the AGN coming out of the host galaxy, and we think those jets extend onto very large scales, impact this gas and keep it hot ionized. And on galaxy scales, which I'm going to be focusing on today, we see these observed relations between the properties of the central regions of galaxies, like for example the bulge velocity dispersion, and the mass of the supermassive black hole. It's a very nice, tight, linear relationship. And we can only explain the form and tightness of this relationship if the black hole is having some impact on the central regions of galaxies. So we see on all scales here that AGN are having an impact on the host galaxies, and we call this process AGN feedback. So like I said, I'm going to be focusing today on galaxy scales, so by that I mean kiloparsec scales. And the main way we think that AGN influence their galaxies on their scales is by driving outflows of gas. So by outflows of gas, I'm talking about bulk motions of gas accelerated to velocities of thousands of kilometers per second in some way by the AGN. So there's two main ways we think AGN can do this. One is via the accretion disk. So the accretion disk is incredibly bright, and that means it produces an incredible amount of radiation pressure on the surrounding gas in the narrow line region, or broad line region. This gas is then accelerated away from the central AGN via radiation pressure, again to velocities of thousands of kilometers per second. We also have jets from AGN, these very fast, highly collimated structures of plasma. On kiloparsec scales, we think these jets, and we observe this, these jets can impact the interstellar medium of their host galaxies. As they do so, they drive shocks into the gas. Gas is accelerated by these shocks and heated up. So in both cases here, we have gas accelerated to thousands of kilometers per second by either an accretion disk or the jet. It's unclear which of these is most important, as it were, for galaxy evolution. But we know this, well, we think this is important, because what we think this can do is can heat up and remove gas from the central regions of galaxies that is needed to form stars. Okay? And if you're preventing star formation on these scales, then you are fundamentally changing how that galaxy is evolving, because a galaxy with these processes will have a very different stellar populations at the present time compared to a galaxy that's not undergoing these processes over billions of years. So this is all very nice, and if we look at simulations, we require these processes to be implemented in order to reproduce the observed properties of the local galaxy population. The problem comes in actually deriving the properties of these outflows from observation, because that's actually very, very difficult. So what I would argue is the single largest source of uncertainty in doing this, in deriving the properties of these AGN-driven outflows from observations, is the electron density of the ionized gas. So we see these outflows in ionized gas at temperatures of around 10,000 degrees Kelvin, traced by optical emission lines like O3 and H alpha. And when we're trying to calculate the key parameters of these outflows, the single biggest source of uncertainty is the electron density of the gas. So basically how many electrons there are per unit volume. Now the reason this is important is because when we are calculating the parameters we need, so what we're talking about here to compare to observations, we're mainly talking about mass outflow rates. So that is how much material is being carried by an outflow per unit time, or how much mass is being carried by an outflow per unit time, and the kinetic power of the outflows. That's the kinetic energy per unit time that the outflows carry. To calculate these properties, we need the outflow mass. And the outflow mass depends on several things. So easily observed properties like the luminosity of the emission line, and then we have the electron density, along with constants like the proton mass, the recombination coefficient, which is known from atomic physics very well, and then the frequency of the emission line you're using for this calculation. But here you can see that the outflow mass depends inversely on the electron density. And the electron density is largely unconstrained. Then to calculate the mass outflow rate, we require a constant, which depends on the geometry of the outflow, the outflow velocity, and the outflow radius. But again, depends on the outflow mass, which again depends on electron density inversely. And then to calculate the outflow kinetic power, we require the mass outflow rate and the outflow velocity. The key point here is that all of these parameters are inversely proportional to the outflow electron density. Okay? Now, why is that important? Well, this is important because the most commonly used method to calculate out the outflow electron density involves measuring two emission lines from a sulfur-2 ion. So what we do is we take a spectrum of an AGN outflow. So here's the typical spectrum. On the x-axis we have wavelength, and on the y-axis we have flux. And we see this doublet of emission lines arising from sulfur-2. The way we know that this works is from atomic physics. The relative amounts of flux in these lines depend on the electron density of the outflowing gas. So if you look at the plot down here, on the x-axis we have the log of the electron density, and on the y-axis we have the ratio of the fluxes in these emission lines. And as you can see, as the electron density increases, this ratio changes. So what you do is you take your spectrum, you measure the flux ratio of these two lines, so the relative peaks of these two lines, effectively, and then you plot that on here to get your electron density. Now, there's a key problem here, and that is that this technique is only strongly sensitive up to densities of around 10 to the 3 electrons per centimeter cubed. Beyond this point, this curve starts to flatten or asymptote. So unless you have incredibly sensitive observations, so high Stirling observations, if your outflow has a high density, so above 10 to the 4 electrons per centimeter cubed, say, you could significantly underpredict your outflow density because you would have a very highly uncertain ratio, so you have an uncertain electron density, and typically what we see happening is people measure electron densities which are around where this curve is sensitive to. And the problem here is that's likely just an error in the measurements, right? Because what's happening potentially in some cases is the electron density is very high, but because of this technique not being very sensitive at high densities, authors end up measuring quite low electron densities and significantly underpredict the electron densities of these outflows. And again, because the key parameters we're interested in, the mass outflow rate and kinetic power are inversely proportional to electron density. That means if you're over-predicting your electron density with this technique, you will be significantly, if you're under-predicting your electron density with this technique, you will be significantly over-predicting your mass outflow rates and kinetic powers. And in doing so, you will be significantly over-predicting the impact that these outflows are having on their host galaxies. So it's important that we constrain this. So the technique we've used in the past to address this involves using fainter emission lines, so harder to detect emission lines, of sulfur 2 and oxygen 2. So singly ionized sulfur and singly ionized oxygen. So in this technique, which we call the lines involve transauroral lines for historic reasons, what we do is we measure the flux ratios of various doublets in our spectra for our outflows, and we plot these flux ratios on the x-axis here and on the y-axis here. And you can see here these measured points are the measured values of these emission line flux ratios for various outflows in different AGN. What we then do is we simulate a range of gas clouds being photoionized by a central AGN with photoionization code. So we have a gas cloud in our model, we ionize it with a central ionizing source, and then from there we get out a predicted value for these emission line flux ratios. And then we do this for gas clouds of different density and different color excess. So what the spectra allows us to do is we have our black grid of points here, which are the simulated emission line flux ratios for gas clouds of different density and effects of extinction. And we can simply compare our measured points to those from our simulations, from our models. And in doing this, we're able to get electron density values out, measure electron densities. And the key advantage of doing this is this technique is sensitive to a much wider range of electron density values than the sulfur 2 technique is. So if your outflows indeed have electron densities of, say, around 10 to the 4.5 electrons per centimeter cubed, you will actually measure densities of around those values. Whereas with the commonly used technique, you would end up measuring electron densities that are potentially orders of magnitude lower. And again, because there's inverse relationship between outflow power and electron density, that means you would be over-predicting your outflow powers by potentially orders of magnitude. So when we go out and do this, so this is work I did in my PhD, we were able to use spatially resolved observations for several nearby galaxies and use both of these methods to verify if this is indeed a problem. So for example, in the galaxy IC5063, with the sulfur 2 technique, we measured electron density of around 10 to the 2.8 electrons per centimeter cubed, whereas with this newer transauroral line technique, which I'm arguing is more sensitive to outflowing gas, or is a better probe of outflowing gas density, we measure electron densities that are around half an order of magnitude larger. This seems to be even worse in the case of a very well-known AGN, NGC 1068, where if we measure electron densities with the commonly used technique, we get a density of around 10 to the 3 electrons per centimeter cubed, whereas with this transauroral line technique, we find electron densities that are up to 2 orders of magnitude larger than this. So again, this is important because the key properties we're interested in to measure the impact of the outflows on the host galaxy, the mass outflow rate and kinetic powers, are inversely proportional to electron density. So because the electron densities with the common use technique have been under-predicting values by 2 orders of magnitude, that means the past observations have been over-predicting the power of outflows by orders of magnitude, which completely changes our interpretation of the impact of these outflows on the host galaxies and thus the interpretation of how these outflows are affecting the evolution of those galaxies. So with our more precise electron density measurements in hand from our transauroral line technique, again this newer technique, we're able to calculate precise mass outflow rates and kinetic powers for the outflows in these objects. So we find mass outflow rates of anywhere from a fraction of solar mass per year to several solar masses per year, which is quite modest compared to what many authors have found in the past. And when we calculate kinetic powers with these electron densities, we find that the kinetic powers are typically up to about 1% of the volumetric luminosity of the host AGN. Now, I've sort of parameterized kinetic power in this way because that's very commonly done in outflow studies. Typical values, as measured by studies that use non-precise electron density measurements, are between 0.5 to 10% of the AGN luminosity we're finding kinetic powers which are on the bottom end or far below this range. So the interpretation here is if we use precise electron density diagnostics, we find that actually outflows don't seem to be having much impact on the host galaxies, which completely changes our interpretation of the importance of these things in galaxy evolution. Okay, so that's all great, but that's 3 galaxies, right? It's not exactly representative of the galaxy population. So work we've done recently is to extend this to larger samples to really hone in on the comparison of these 2 different electron density techniques and see what's going on. Is this simply the fact that the techniques have different sensitivity ranges, or is there something deeper regarding the interpretation of these lines that we're using in the different techniques? So what we're able to do is take a sample of 48 type 2 AGN. So in this case, we're only seeing emission from the narrow line region. So we're not seeing the AGN itself, just the gases ionizing. And for the outflows, we're able to measure the electron densities, both using the trans-auroral line technique. Again, that's the technique that I'm arguing is more sensitive. So a wide range of densities. So we plot the log values of that on the x-axis. On the y-axis, we have values for the same outflows as measured with the traditional commonly used sulfur 2 technique. So here, every grey contour is effectively a probability density function for individual objects. So again, there's 48 objects here, where the contours here represent 67%, where we think that in these areas we are 67% confident. That's where the values of the electron densities for 2 techniques lie, for individual objects. And the black contours here contain 10, 30, 50, 70, and 90% of the probability density functions for all of the objects. So again, we see here that these contours lie far away from the one-to-one line, which is here in red. So if these 2 techniques were measuring the same thing, we would expect this distribution to fall along this one-to-one line. We can see it is systematically offset towards higher values of densities from the trans-auroral lines. So this is telling us that even within the range where both of these techniques are sensitive, again, kind of around here, there is still a systematic offset between the electron densities that you measure between the 2. And that's indicating a different physical origin for the emission lines involved in these 2 different techniques. And again, when we calculate the difference between the techniques on average, between the densities given by the 2 different techniques, we find it is around 0.75 orders of magnitude. So even apart from the uncertainties involved in the sulfur 2 technique, there are deeper physical interpretation about what's happening, where these lines are coming from, which again could impact our determined values for electron densities. So the interpretation here that we're favouring based on this and other arguments, previous detailed arguments that I've made in past work using more detailed observations, is that if we were to take a single cloud in a narrow line region of an AGN, and we would zoom in on it, what I am arguing is happening here is that in a single cloud, the trans-auroral lines, which again are giving denser electron density values for the same gas by about 0.75 orders of magnitude, I'm arguing these lines are being emitted by denser regions of a given gas cloud or complex of gas clouds than the sulfur 2 technique, again the commonly used technique. And crucially, based on various arguments involving nebular physics, I'm arguing in this case the denser gas is a better representation of the outflowing gas in these systems than the lesser dense gas traced by the sulfur 2 lines. So the key point of all of this is that if you want to do AGN outflow studies, you cannot just use the sulfur 2 lines because you'll be underpredicting your electron densities by at least around 0.75 orders of magnitude due to this intrinsic physical effect. And that's not even talking about the fact that technique is not sensitive to higher electron densities that we have actually measured for outflows in other systems. The problem here is that the trans-auroral lines are quite faint, so it's quite hard to measure those in typical AGN spectra. So what we're able to do is plot the density distributions from these 2 different techniques. So the blue here is the density distribution from the trans-auroral lines, and the yellow here is the electron density distribution from the sulfur 2 lines. And we're able to use the difference of the means of these 2 distributions to effectively produce a correction factor that we can add onto sulfur-2 density measurements to produce a distribution here in red, which statistically speaking is indistinguishable from that produced by the transauroral lines. So this still needs to be verified because this is only produced for one sample. But what we're saying here is if you're unable to use the more accurate transauroral line technique because you don't have the lines in your spectrum, you could use, as a way to get a better estimate of the electron densities, the sulfur-2 technique, which uses brighter lines and add a correction factor of about 0.75 orders of magnitude to produce electron densities that are more descriptive of outflowing gas. And will give you values that aren't under predicting electron densities by such a large amount. Okay, so we have this technique in hand. Now this is important because very, very soon, and actually as of now, we have several large optical spectroscopic surveys observing millions of AGN. Okay, so that means that we can start applying these techniques to those spectra from those surveys to start really characterizing outflows in very large numbers. But as I said, the transauroral lines here are quite faint, so we will not expect to detect them in the majority of cases. So we can use the sulfur-2 technique and this correction factor to get outflow densities which are more characteristic or more representative of the true outflow electron density in order to derive more robust estimates of key outflow properties, again, mass outflow rates, kinetic powers, in order to interpret the impact these outflows are having on their host galaxies. This has been attempted before. So we can see here two quite famous studies in this field. So these use observations of thousands or tens of thousands of AGN to try and characterize the impact that outflows are having on the host galaxies. So on the left here we have the main result of Millennia et al. 2013. So these authors took a sample of around 24,000 quasars, type 2 AGN, and what they have here is the cumulative fraction of velocity values, measured velocity values for the spectra of these galaxies or these AGN, and they split these up into low radial luminosity and high radial luminosity. So the interpretation here is that the red line, which represents the higher radial luminosity bin, on average shows much larger velocities of the ionized gas than the sort of less radioluminous objects. Because the jets produced by AGN produce a lot of radio emission, the interpretation of this in the past has been that, well, since the stuff with more radio emission seems to have more disturbed gas, this would indicate that jets are the main driving source of the outflows, right? Because you see a relation here between the radioluminosity and the disturbance of the outflows, or the more kinematic picture of outflows. So since the jets are producing radio emission, this is evidence has been taken, this is evidence of jets being the main driver of AGN outflows. On the other hand, we have another study by Fiore et al. 2017. What these authors did is take an aggregation of mass outflow rates from various studies in the past. They assumed a single value for the electron density, and from this they were able to calculate mass outflow rates for thousands of objects, and then they plotted these mass outflow rates against the bolometric luminosity of the AGN. So that's the total integrated luminosity of the AGN. And you see they found these linear relationships between AGN bolometric luminosity and mass outflow rate. And the interpretation here by a lot of people since has been, well, since for a more luminous AGN you would expect more radiation pressure from the accretion disk, we're seeing here, since as you increase that radiation pressure effectively, the mass outflow rate increases. Well, this is showing that the main driver of outflow is actually radiation pressure. So again, to summarize here, in the past, we're seeing here, this has been taken as evidence that jets are the main driving mechanism for outflows, and here we're seeing that the radiation pressure of the accretion disk is the main outflow driving mechanism. Oops, sorry. And again, at least in the Fiore case, the interpretation based on the values of the mass outflow rates is that outflows are important for the evolution of galaxies. So actually, if you take these mass outflow rates, that would indicate outflows are having an impact on the host galaxies. The problem here is that in both cases, these studies use samples of AGN that were optically selected. So rather than just getting spectroscopy of random sources, they first did a photometric survey, so they saw the optically bright stuff and then followed those up with spectroscopy. So that means that these samples we're seeing consist of optically bright AGN. there could be an entire population of optically faint AGN that are very bright at radio wavelengths that is being missed entirely by these sources. So effectively, these samples are biased towards optically luminous AGN. Similarly, at least in the case of the Fiore study, for all these mass outflow rates, they assumed a single value for the electron density. And as I've shown, the electron density values seem to change by orders of magnitude between different AGN outflows. So these studies are fantastic, and they really reveal a lot about the nature of these outflows, but to really get a comprehensive picture and an accurate picture of how these outflows are impacting the host galaxies on a population level, we need to make sure our samples that we're using to do this aren't biased, and we need to make sure that we're using precise diagnostics of key parameters like the electron density, like I just showed you. So, with the new upcoming WEAVE-LOFAR survey, we're aiming to address this. So WEAVE-LOFAR effectively is going to use the new WEAVE optical spectroscopy facility on the William Herschel telescope in La Palma to follow up millions of sources detected by the LOFAR array. So LOFAR is a low-frequency radio interferometric array across Northern Europe. As of now, it has effectively covered the entire northern sky at frequencies of around 144 megahertz. So with WEAVE has what we call a multi-object spectroscopy mode. So effectively, it can detect in a single pointing, it can get spectra of around 1,000 objects, 1,000 sources. So the idea with WEAVE-LOFAR is that we're going to follow up radio sources detected by LOFAR at low frequencies to get optical spectroscopies of those sources with WEAVE. This is important because that fundamentally means that our selection criteria for our samples will be radio selected. Optical selection is heavily influenced by the presence of dust in galaxies because light at optical wavelengths is reddened or extincted by dust. With radio, you don't have that problem. Radio is effectively extinction free, so you can detect sources evenly in heavily obscured systems. And again, the source of the radio emission at these frequencies is dominated or almost entirely due to the activity. So by activity here, I'm talking about things that may influence host galaxies, namely star formation or AGN. Again, radio jets, for example, produce a lot of radio emission. So we'll be detecting systems in a much more representative way that's much more representative of the overall AGN population. WEAVE-LOFAR is expected to start later this year. Depends slightly on how things go with the WEAVE instrument. But we're doing a lot of the groundwork to make sure when this starts, we're going to hit the ground running and really start pumping out these results quite quickly, which I want to talk to you about in a minute. And the end result of WEAVE-LOFAR is we'll have over 1 million spectra of galaxies and AGN that have been radio selected. Again, selected based on activity, which in a way that is effectively extinction free. And this is orders of magnitude more than past radio selected surveys. And crucially, the instrumental properties of WEAVE means that we'll be able to apply these accurate outflow diagnostics, for example, the electron density technique that I talked about before, to WEAVE data to get outflow properties for hopefully tens of thousands of AGN. So we can really do this in a population level way. But to do that, we need to make sure that we are actually picking out samples from the WEAVE-LOFAR survey that are representative of different galaxy populations to make sure we're not biasing our results in different ways. So the typical way we do this is to make sure that we are classifying our galaxies robustly before we start analysing the outflows in them. So the way we do this, effectively, if you imagine here, you're on the vertical axis, you have objects that have no radio excess relative to what we'd expect from star formation. So down here you have objects where effectively the radio emission is not above what we'd expect from star formation, whereas up here we have objects where we have an excess of radio emission beyond what we can simply get from star formation. On the x-axis here, or horizontally, we have stuff which is what we call low excitation based on its optical properties. So that's stuff that has very low ionization emission lines, and here we have high excitation stuff, so stuff which has quite highly ionized emission lines. And in each quadrant here, we have different classes of galaxies. So, for example, low optical excitation stuff with no radio excess compared to star formation, or based on what we expect for star formation, we have what we call star-forming galaxies. So galaxies where the radio emission is dominated by star formation. Here, for the stuff where we see high excitation optical emission lines that we can only explain via AGN, but we don't see radio excess, we call these radio quiet AGN. And then stuff that has a radio excess, indicating that the radio emission is dominated by AGN, we have low excitation radio galaxies, so stuff like AGN or liners, which are a class of objects which show radio emission in many cases, but quite weak or quite low ionization spectra, and then high excitation stuff. So these are your typical sort of classical AGN stuff like CFLITs and quasars. So we want to classify each object in the WEAVE-LOFAR survey into one of these bins to make sure we're having representative samples of AGN to analyze. So we've done this the way we've, the classification scheme we developed at Hertfordshire to do this robustly is based on two key diagnostics. So on the left here we have a relation between the radio frequency, so at LOFAR frequencies, again around 144 megahertz, against the luminosity of H alpha, so emission line. Effectively, because the radio emission here is dominated, we'd expect for a star-forming galaxy by supernovae, we'd expect a linear relationship between the radio luminosity and the H alpha luminosity. And you see here, we find this locus of points, and this is what we'd expect for objects that are dominated by star formation. And anything that has a higher radio luminosity, that are given H alpha luminosity for this, we call radio excess sources, where we can only explain this radio excess by the presence of an AGN. We also use from WEAVE, from the optical spectra, what we call a BPT diagram. Effectively here we have two emission line ratios, one at nitrogen 2 and H alpha on the x-axis, and one at O3 and H beta on the y-axis. And effectively, due to different nebular physics reasons, we'd expect star-forming galaxies to lie down here, where we'd expect AGN to lie in this region up here, with the high excitation AGN, so again, stuff showing strong, high ionization emission lines, things like O3, we expect up here, and low excitation AGN falling down here, so stuff with strong, low ionization emission lines, but fairly weak, high ionization emission lines. So by placing a given object on these two plots, we're able to determine what class of AGN or galaxy it is, and therefore determine the main driver of its activity. So for example, if we had a galaxy where its radio luminosity and H alpha luminosity fell in this region of this diagram, we would see that it has a radio excess relative to what we'd expect just from star formation, so we know that it's an AGN, because that radio emission can only be explained by AGN. And if we found that its optical emission line ratios fell in this region, we'd see that it's high ionization, high excitation, so we would call this a radio loud, high excitation AGN. Likewise, if we saw something where its radio excess, didn't have a radio excess and its value on this plot fell where we'd expect a star formation, we might expect based on this plot alone that this is simply a star-forming galaxy. Whereas when we use our information from WEAVE with the optical spectra, we see that its emission line ratios can only be explained by an AGN. So we'd call this a radio quiet AGN. So by effectively producing a point on each of these diagrams 10,000 times for a given object, where again the position on this diagram depends on various observational uncertainties from WEAVE spectra, from LOFAR observations, for example, we're able to produce effectively a contour of where we'd expect these objects to fall on these two diagrams. So you see here the shaded red region is where, if we did this 10,000 times, the region where we'd expect the points to fall based on the observational uncertainties. And then simply what we do is we count the number of those 10,000, or the fraction of those 10,000 random draws from the observations, and we say, okay, what fraction falls in a given region of these diagrams? And in doing so, let's say if here 20% fell in the radio excess region and 80% fell in the star formation region, then we could say with 80% confidence, the radio emission is dominated by star formation, whereas here you'd see that basically all the draws fell in the AGN region of this diagram, so we could say that with 100% confidence, the optical classification here is an AGN. So in doing this, we're able to robustly classify our galaxies because we're able to produce a classification for each galaxy where we can only select, for example, sources where we are 95% confident in the classification. So that means we can have very, very pure samples of these different galaxy classes, and then we're able to apply our precise outflow-diagnostic techniques to those samples to start determining how do the properties of outflows vary within them. And this allows representative studies of the AGN population. Okay, so what's the next step once we've done this? Again, that classification technique is ready to go, and we've tested it. There's an upcoming paper by Marina Arnaud from Hearts that's done this, and there's already a paper by Alyssa Drake from the Hertfordshire group that has done this for a different sample of galaxies from based on FTSS spectra. So that technique is ready. As I was talking about earlier, our precise outflow-diagnostic techniques, again, things like electron densities, that's ready to go. So when we start getting WEAVE-LOFAR spectra, we're able to determine things like, for example, mass outflow rates for representative samples of each type of these AGN. And we're able to do things like this, for example. So here we have a simulation of radiatively driven outflows, so outflows launched by the accretion disk, by radiation pressure. And this study was able to predict observed mass outflow rates and how that varies against the luminosity of the AGN. And you see they predict this linear relationship. So with our WEAVE-LOFAR spectra, we'd be able to actually plot this accurately and see, do our observations line up with what is predicted by different theoretical models? And in doing that, we'll be able to determine how are these outflows accelerated. Again, that's a big unanswered question in this field. And if we see, for example, a relationship like this, then that will be very strong evidence that these outflows are accelerated by radiation pressure rather than by the jets. And that's important because then we can tell cosmological simulators, look, for your AGN feedback prescriptions in your models, you need to include AGN radiation pressure more so than you do the jets on small scales. Of course, you still need the jets on large scales, but on galaxy scales, it would seem if this is the case, radiation is the dominant driving force. Likewise, again, the hope is we'll be able to get some papers out, or of us collaborate with some theorists at Hertfordshire and in other institutions to produce relations like this based on what we'd expect if radio jets on kiloparsec scale with a driving mechanism. And in doing that, hopefully those relationships will be different, and we'll be able to use these to distinguish between what is the main driving source or the main driving mechanism of AGN outflows on population level. And of course, as well, because we'll have mass outflow rates at every one of our sources, and we'll have accurate kinetic powers, we'll be able to compare to other sort of cosmological scale simulations and to compare to the predictions of those simulations to determine are the mass outflow rates that we measure sufficient for those simulations in order to explain the properties of the galaxy population. So effectively, in reality, are the outflows as powerful as the simulations require them to be? Or is there some fundamental misunderstanding in our models of galaxy evolution? So I'll finish there. Just to summarise, with large spectroscopic surveys, so those, for example, that already exist, like DESI, but in particular the WEAVE-LOFAR survey, which is going to start hopefully in a few months' time, we'll be able to perform the first representative population-level studies of galactic scale AGN feedback. And again, by that I mean mainly driven by AGN-driven outflows. To do this properly, we require precise electron density measurements. So again, with the techniques I've talked about, either with the transauroral lines, which are quite faint, or using the commonly used bright line sort of 2 technique with a correction factor of around 0.75 dex, or orders of magnitude that I showed earlier. We'll need radio-selected samples, again, samples that are based mainly on the activity rather than high optical brightness as previous surveys. And the key driver here to do this will be the WEAVE-LOFAR survey, or rather the key thing that will enable this is WEAVE-LOFAR. And then again, to make sure that we're having representative samples, or samples that are representative of the population, we'll need a robust way to classify those sources from WEAVE-LOFAR, and that's the way that's already been developed at Hertfordshire with these 2 key diagnostics, and doing this in a probabilistic way. So I'm happy to take any questions. Again, thank you very much for inviting me here. It's been great to talk to you all. And yeah, thank you very much for your attention.
Thank you very much. Amazing talk.
Thank you.
So, time for questions. Sergio?
In the sulfur transauroral line measurement, you are measuring 2 different electron densities from different regions. But in your equation for mass, kinetic energy, you have only one electron density. So you have to, you say that the electron densities measured with transaurora lines are more representative of the overall electron density of the emission line regions. But why? You need to have a profile of the region, saying, and you have something like that.
Effectively, yes. So I don't think I have slides to show this, unfortunately. But in past work of a galaxy, so in my PhD, I did a study of a well-known galaxy called IC5063, which presents clear outflows driven by a jet. And we took very high spatial resolution X-future observations. And by isolating the emission from the outflowing gas, so again, the high velocity gas, and effectively taking spatial flux profiles, so effectively the amount of flux in each emission line to the outflows as a function of radial distance from the AGN, we saw that the transauroral lines have the same spatial flux distribution as key lines like O3, which we are typically using for the outflow kinematics. So that's telling us that transauroral lines are emitted in the same location as the other lines that are being used to diagnose information about the kinematics of the outflow. So we know they're emitted by the same clouds, and based on quite a detailed nebular physics study where we sort of bring in knowledge of the structure of gas clouds, particularly with critical densities, we argue that in a given gas cloud you will have a basically regions of different electron density. Okay, so now the structure of those clouds isn't quite clear, so we can't resolve them directly because they're very, very small, right, probably parsec scales, but we know that the O3 lines, which are used for the kinematics for the outflows, have quite a high critical density. The commonly used sulfur 2 lines, those that boost the ratio, they're quite a low critical density. Whereas the critical density of the transauroral lines is closer to O3 than the sulfur 2 lines are. And again, as effectively the critical density means that as you have gas close to that critical density, you will have, if you have a given critical density for an emission line, that emission line will become brighter the closer the gas is to that density, okay? So in doing those two things, again, showing that the emission lines are produced by the same gas clouds, and this argument based on the densities of the different lines, we argue that effectively we're tracing the same gas, but we're tracing parts of that gas with transauroral lines that have a density similar to that of the gas of the emission lines that we are using to get the kinematics. Does that answer the question?
Yeah.
Thanks.
So, do you need to have high spectral resolution in order to use your new method? I mean, for example, when you use the mass outflow rate, you have H beta, and H beta can have a contribution coming from the AGN of the star formation.
Yeah.
So, in this case, these lines, you can use the integrated value of the flat, or you need also to discriminate between two components?
Fantastic question. So, with the sulfur 2 lines, I don't think I actually have a protection of transauroral lines.
Yeah, because I was wondering about your sample, and
it's a fantastic question. This is another key advantage of the transauroral lines. Okay, so the sulfur 2 lines, as you correctly mentioned, you require resolving the lines in the doublet. Okay, now as you have outflow kinematics, these lines will broaden, right? So you effectively, in many cases for outflows, you just get kind of a blob here. It's impossible to distinguish between the 2 lines. Another key advantage of the transauroral line technique, and again, I'm sorry I don't have a spectrum to show you here, is that effectively what you do is for these ratios, rather than measuring the individual lines in a doublet, all you need is the total flux in the doublet. So for example, on the x-axis here, you have the total flux of that sulfur 2 doublet compared to the total flux of a different doublet. So in the case of outflowing gas, again, this is another reason the lines aren't blended as much. Well, sorry, the lines, if you have lines that are blended, you can still use transauroral line technique.
Okay, so it's a very nice one.
Yeah, so that's a really good point. Thank you.
Did you also explore the method, the ionization method by Baron and Netzer for the derivation of the electron density and compare with your results?
Absolutely, yeah. So we haven't been able to do that for their objects. If I remember right, their object's quite dusty, so it's hard to get. Well, actually, it's a good point. We haven't done that for objects yet. Maybe we should look into that. But yeah, so basically, there's some fantastic authors, Dale Baron and Hagai Netzer, who developed a different technique, effectively involving the infrared SED of the dust in an AGN system. and used that with ionization parameters effectively to very cleverly calculate the electron density of the ionized gas, the outflowing ionized gas. And again, they find very high electron densities, kind of around 10 to the 4, 10 to the 5 electrons per centimeter cubed. So again, that's a completely different technique involving completely different diagnostics. And when they do that, again, for different systems, but they're finding, again, very, very high electron densities, which agrees with what we're finding here. But yeah, we haven't done that for their systems, but that'll be definitely something interesting to do. But yeah, that definitely gives us confidence that we're on the right lines here. Yeah.
And when you mention your type 2 AGN and then derive the factor to correct the electron density here, do you think, or do you have any plan to derive this factor for type 1 AGN? Do you think it could be similar factor? Because it is very useful for the derivation of the real.
Yeah, so that's something that we're going to look into again. With WEAVE-LOFAR, we don't know exactly how many type 1 AGN we'll have. We're currently looking at DESI, so DESI is another cosmological survey. And they're going to do fantastic cosmology, but we're basically going to use their spectra to do AGN studies instead. That's basically with DESI we're doing this already, and we're seeing that we have quite a few, probably tens of thousands of type 1 AGN. And again, hopefully with WEAVE-LOFAR will have the same. So yeah, it'll be interesting to see how this correction factor varies, not only between type 1 and type 2, but with different types of objects. Again, I mean, the point I want to make quite clearly here is, okay, we can use this correction factor kind of in general to get an estimate, but I do really want to reinforce this is just an estimate. And the value of this could very well change depending on the sample of aging you're looking at. But yeah, one thing we're going to do is look at how this correction factor changes for different samples, so quasars, CFERTs, low ionization stuff, and then of course type 1, type 2 AGN. Yeah, but we don't know exactly how that would vary, but yeah, it's a really point.
Are you planning maybe to also use, I don't know, molecular outflows, and also, because I think that the values that you were showing before were for ionized gas.
Yes, right.
But I don't know if you, for example, are planning to do in the future something with molecular or neutral. Just to know, because you said that you were in the lower value of the mass outflow rate, and that we were overestimating these values, but I don't know if in other phases of the ISM will happen the same or not.
Yeah, so again, it's a really good point. So just to be clear for everyone here, when we look at outflows, we see them in different phases. So by phases, we mean gas of different temperatures and effectively compositions. So we see this from highly ionized stuff, from X-ray absorption, which is really badly constrained because it's really hard to observe. We see stuff which is like atomic, so around 10 to 100 to a few thousand degrees Kelvin. And then we see this cold molecular stuff at a few hundred degrees Kelvin that you were just talking about. And we see in objects, in many cases, all of these outflow phases happening. And the kicker of all of this is that for different objects, we see that these different phases tend to be dominant, right? So it's something, a given object, you might have the vast majority of the mass is in the raw ionized phase, in others it's in the cold molecular phase. Yeah, this is definitely something we need to consider when we're doing this on a large scale. The problem would be getting kind of enough ALMA time to get millions of observations to cold molecular. I'd love to do that, but I don't think that's going to happen. But yeah, it's something that we're thinking about. What would be ideal would be if we could have like a universal sort of ratio between, let's say, warm ionized mass and cold molecular mass, but that definitely doesn't exist because the objects we've looked at, again, the objects I showed earlier, we've done this trans-raw line technique. We've seen that the cold molecular gas relative to the warm ionized gas mass is just highly variable, right? It's like varies by orders of magnitude. So yeah, that's a really good point. It's kind of unclear, but hopefully it's something we can start.
I mean, you can only find the best data.
Yeah. Well, again, hopefully what we can get to really on a timescale of a few years, and other people working on this, is if we can have the theorists sort of, be wizards and solve this for us magically. Maybe they can say for a given type of system, for example, maybe for like, in the case where you have a jet driving the outflows, maybe there is some sort of expected amount of molecular gas compared to ionized gas. That's a problem because of cooling and things, but yeah, maybe we can start answering this question, but it's something that's probably a way off just yet. But yeah, it's a really good point.
Thanks.
Yeah.
Any other questions?
Maybe just in general on this point, I guess, for the overall feedback effect, how important really are these small, dense clouds? Because I imagine their volume filling factor is quite low.
Yeah.
So is there just like some scaling relationships that say, okay, if you can push a small cloud of gas at that velocity, then the ambient gas is driven more?
Yeah. So it's a very, very sort of complex scenario. So again, this isn't a cop-out answer, but these systems are highly complex. In often case, we're resolving hundreds of parsecs at a time, so it's like a large rate of gas. The key point we're making is that we would expect the bulk of the gas, or rather, think of a way to phrase this, we expect the densities we're driving and the mass outflow we're driving to be characteristic of the overall gas flow. There has been an argument in the past that, as you say, we are tracing particularly dense clumps of gas, and it's, for example, what you might have is a very large complex of outflowing gas, which is very low density and high mass, but then we have these very, very dense clumps that we're tracing with the transmural lines, right? We have looked at this, so there's a system here that I looked at with Muse, where we tried our best to sort of look for this. So we took a quasar where we know there are compact outflows that are very powerful, like mass outflow rates of tens of solar masses per year in the ionized emission. And to test this idea, if there is like a larger factor, low density, high mass component to those outflows, we tried to spatially resolve it and we didn't see anything. And because we didn't detect any low density emission on large scales, we're able to put an upper limit on what this kind of low density component might be, and it comes out to like a fraction of solar mass per year in terms of mass outflow rate. Now that's one system, and we do need to do this for other systems, but I haven't seen any convincing evidence that there is this sort of, extended low density component to these outflows. So I think we're definitely, on the right lines with using these transfer line techniques. Does that answer the question? Yeah. Thanks.
And are you going to explore also low power rally jet and your WEAVE sorry?
Yeah, for sure. Well, with WEAVE-LOFAR, again, we sort of know this based on LOFAR already. Where's the plot? Sorry, there it is. We fully expect. I think there already has been a study by Emmy Scott looking at this, where she effectively reproduced this plot with, for an optically selected sample effectively. So it was LOFAR observations cross-matched with SDSS spectroscopy, and she effectively found this relationship again. So yeah, we definitely have a lot of sort of intermediate or low radio power sources, and the hope is that we'll be able to do this with WEAVE-LOFAR in a way which is radio selected, and not just get these velocities, but also get mass outflow rates. So yeah, that's definitely the expectation.
So a lot of work to
Absolutely, yeah. Look, I've got 2 years left on my current postdoc, so see where we go. Yeah.
Any other questions? Any questions online? Well, if not, I think we stop here. Next time to look again.
Thank you.